Hello everyone, so in this lecture we are going to prove the theorem that every Euclidean ring is a principal ideal ring. For proving this theorem, we need to know about that what is Euclidean ring. An integral domain, that is commutative ring with unity without zero divisor. This is the definition of integral domain. An integral domain is said to be Euclidean ring if two conditions were applied. First, a does not equals to 0, b does not equals to 0, then alpha of ab is greater than alpha of a. Second condition, a belonging to r, b belonging to r, b does not equals to 0, a is equals to bq plus r. Then either r will be 0 or alpha of r is less than alpha of b. Here a mapping is defined from a set of non-zero elements of A to a set of non-negative integers of B. Now, returning back to our theorem, prove that every Euclidean ring is a principal ideal ring. That means every ideal belonging to this Euclidean ring is principal ideal. What is principal ideal? It means that every element of an ideal is generated by a single element of that ideal. Or if every element of an ideal can be written in multiple of a single element of belonging to that ideal, then that ideal will be known as principal ideal ring. Principal ideal. Now, for proving every Euclidean ring is a principal ideal ring, let R be an Euclidean ring. Let A be its ideal. First case, if A is equals to 0, that means A is a zero ideal. Zero ideal is a principal ideal ring because every element in a zero ideal can be written in product of 0. That means it is generated by a single element belonging to that ideal. That means it is a principal ideal. If every ideal of R is zero ideal, that means principal ideal. That means Euclidean ring is principal ideal ring. It is already proven. Now second case, if ideal is not zero ideal, then we need to define a mapping from non-zero elements of A to a non-negative integers set such that T is that non-negative integers set which maps every non-zero element of A in it. Now, it is important to remember the point that every non-empty subset of a non-negative integer contains least element. Here, T is a subset, non-empty subset containing non-negative integers from the definition of Euclidean ring. Then it means T will contain a least element. Now let A is that element belonging to A. So A is belonging to A, that means it is not equals to 0 because A is a set of non-zero elements. So alpha of A belonging to T is the least element of T. A is that element of A which when mapped to T, it will give the least element in T. Then how does this statement can be written mathematically? That there exists no x belonging to A. X is belonging to A, that means x does not equals to 0 because we know A is a set of non-zero elements. ऐसा कोई भी x A में belong नहीं करेगा such that alpha of x is less than alpha of A because alpha of A is the least element in T. Now, let any other element be belonging to A such that B does not equals to 0 from the condition. A is already belonging to A. Now, A does not equals to 0, B does not equals to 0 belongs to A. Then, from the second condition of Euclidean ring, B is equals to AQ plus R. This can be written. Then, if B is equals to AQ plus R, from that condition of Euclidean ring, either R is equals to 0 or alpha of R is less than alpha of B. Now, here we already let that B belongs to A. B belongs to A, Q belongs to R, and A belongs to A. Q belonging to R, A belonging to A, then an element can be written as QA because A is an ideal of R. By definition of ideal, B belongs to A, QA belongs to A. From here, it means B minus QA will also belongs to A. Why? A plus is abelian group. From definition of ring or ideal. Now R belonging, if B minus QA belonging to A, that means R belongs to A. If R belongs to A, then letting R does not equals to 0 implies that R equals to 0 or alpha of R is less than alpha of B. If R is not equals to 0, that means alpha of R is less than alpha of, B not, no B. There is a mistake here. A will be taken because in this statement B is equals to AQ plus R and A does not equals to 0. Here A is equals to BQ plus R but B does not equals to 0. Here we can write this. So the condition will change like this. Alpha of R is less than alpha of A. But we already taken here that alpha of A is the least element in T. That means there exists no element in A whose mapping is less than alpha of A. It means this condition is a contradiction. Implies that R is equals to, this condition is a contradiction. It means R is equals to 0. If R is equals to 0, B is equals to AQ. That means an element of T is written in product of A. It means the ideal A is generated by its element A. Hence, A is a principal ideal ring. Proven. Let us summarize that. Firstly, we recall that what is Euclidean ring? An integral domain. What is integral domain? A commutative ring with unity and without zero divisor is said to be Euclidean ring if a mapping may be defined from a set of non-zero elements to a set of non-negative integers such that A does not equals to 0, B does not equals to 0, then alpha of AB is greater than alpha of A. First condition. Second condition, alpha belongs to R, B does not equals to 0 belonging to R. Then A is equals to BQ plus R can be written where Q and R belongs to R. Then either R will be 0 or alpha of R is less than alpha of B. Then we need to prove that every Euclidean ring is a principal ideal ring. If R is an Euclidean ring, it will be a principal ideal ring only when every ideal of R is a principal ideal. Let A be its ideal. If A is equals to 0, that means A is 0 ideal. 0 ideal is a principal ideal ring because every element of a 0 ideal can be written in product of 0. So, if A is a 0 ideal, that means Euclidean ring is a principal ideal ring. Now, second condition, if A does not equals to 0, it means A is not a 0 ideal. Then we need to define a mapping T, where T contains the mapped elements of A, which are not equal to 0. Like this. This is A, this is T. Okay, this is T. Here, all the elements are not equals to 0, which maps in T, or we can say B, which are non-negative. This means T is a set of non-negative integers. Here, this point is very important in accordance to prove this theorem. which tells that every non-empty subset of a non-negative integer contains least element. Let an element belongs to A, which is not equals to 0. Obviously, A is a set of non-zero elements, such that alpha of A belongs to T is the least element in T, according to this point. Then how this thing can be written mathematically? That means there does not exist any element not equals to 0 belongs to A such that its image is less than alpha of A, because alpha is least element in T. Now let any other element belongs to A. Here B does not equals to 0 because A is a set of non-zero elements. Let an element B belongs to A. If here B is a general element in A, then if any general element of A, B can be written in multiple of A. From here, A is already an element of A. If any general element of this A can be written in product of this A, which also belongs to A. This means this A is a principal ideal ring, because like this general element, every element of A which is not equals to 0 can be written in product of this element of A. Let this be A naught. It is very confusing. Okay, let it be A naught. Now it is easy to explain. Now, if any general element of capital A can be written in multiple of this element A naught belonging to A does not equals to 0, then it is clear that this A is a principal ideal ring, because every element of this ideal can be written in product of this element of A. Let B is belonging to A such that B is not equals to 0. A naught is already belonging to A. Then from this condition of Euclidean ring, it can be written like this. Here, if B is equals to A naught Q plus R, then either R is equals to 0 or alpha of R is less than alpha of A naught. B belongs to A, Q belongs to R, and small a belonging to A. A naught belonging to A. Then here Q belongs to R. Already we know. A naught is belonging to A. Then an element Q A naught is may be defined which belongs to A, because A is an ideal. This is by the definition of ideal. If Q belongs to R, A naught belongs to A, then Q A naught will belong to this ideal A. Here B belongs to A, Q naught belongs to A. From here, then B minus Q naught will also belongs to A, because A plus is an abelian group. Obviously B Q A naught is belonging to A, then B or minus Q A naught belong to A. So this can be written by definition of group. If B minus Q A naught belongs to A, this means R belongs. Let here R belongs to A. Now either R will be 0 or alpha of R is less than alpha of A naught. If R is not equals to 0, it means second condition is true. Then alpha of R is less than alpha of A naught, which is a contradiction, because here we already let that alpha of A naught is the least element in T. मतलब कोई भी और ऐसा एलिमेंट एग्जिस्ट नहीं करेगा A में जिसकी मैपिंग अल्फा ऑफ A naught से लेस हो. This means this is a contradiction. So this is a contradiction means this condition will not be applied. So R is equals to 0. If R is equals to 0, then only B is equals to A naught Q. That means B is written in product of A naught. It means that a general element of A is written in multiple or product of this element A naught of A, then every element of A can be written like this in product of A naught. So this ideal A is generated by element A naught, because every element of this A is written in multiple of this element A naught of A. A naught belongs to A and A naught does not equals to 0. Hence, A is a principal ideal ring proven. Thank you.